Welcome to another podcast. In this episode, we're going to be taking a look at limits that involve infinity. And I just want to make this video about some limits that you should probably memorize. I'm going to look at some reasons why they are what they are, but after watching this video and reading through the text, I think you should probably try to commit these to memory so that they're right there at the tip of your mind when you work some problems that actually use these ideas. So a limit at infinity is one of two things. Either the limit as x approaches a value becomes infinite. If that happens, then we say that the point x equal to a is a vertical asymptote. Or the other possibility is the limit itself is infinite, meaning you're looking at the limit as x goes to plus or minus infinity, and that equals some value L. Then the value L, which is a y value here, is a horizontal asymptote. Now there are other possibilities. In order for this to be considered a horizontal asymptote, L can't be infinity, but the absolute value of L, so it can't be positive or negative infinity. But in general, you could have limits as x goes to infinity of some function be infinity. Those are neither horizontal nor vertical asymptotes. We typically call that end behavior. So the limit as x goes to infinity of a function f of x, that could be positive or negative infinity, and that's just part of the ending behavior, generally, of the function. And we'll talk more about ending behavior as we go through this. So here come the things that I basically want you to have memorized or committed to memory from this specific talk. We're going to start with the limit as x goes to 0 from the right of the natural log function. Now that particular limit is going to be equal to negative infinity, and the easiest way to see it is I'm just going to sketch a graph of this. So the natural log function looks like this. And so you can clearly see that as x goes to 0 from the right, the natural log function goes to negative infinity, and as x goes to infinity, natural log also goes to infinity. So that's part of its ending behavior, this one. As x goes to infinity, the natural log function is equal to infinity. So those two things combined, along with the graph here, is sort of an important thing to remember, and that is the behavior of the natural log function in regards to infinity. Similarly, we also want to know about the behavior of the exponential. So if I asked what is the limit as x goes to infinity of e to the x, that's going to be equal to infinity, and the limit as x goes to negative infinity, this one's maybe a little bit surprising for some people, but that limit is 0. So once again, you can kind of see in a graph here, if I was to graph the function e to the x, it looks like this. That's e to the negative x, excuse me. If I was to graph e to the x, it looks like this. Remember, it's the inverse of the natural log. So you can see here as we go to negative infinity, the limit is getting closer to a horizontal asymptote of 0. So this function does have a horizontal asymptote, whereas the natural log has a vertical asymptote. And the ending behavior is infinity. So you should probably try to commit this one to memory also. All right, let's look at another one. The tangent is a really interesting function. So if I was to make a graph of tangent, so I'll just start by writing down a couple of things involving tangent first. It turns out that tangent has many asymptotes. For starters, if you look at the limit as x goes to pi halves from the right, it turns out to be negative infinity. And the limit as x goes to pi halves from the left of tangent turns out to be positive infinity. That doesn't look like a T. Let me erase that. So positive infinity in this direction. The graph here, so if I was to graph this, then remember that tangent is defined as sine divided by cosine. And so tangent will have vertical asymptotes wherever cosine is 0. And cosine is 0 precisely at odd multiples of pi halves. So what you see when you plot the tangent function is at the values pi halves, 3 pi halves, 5 pi halves, negative pi halves, all of these odd multiples of pi halves, the tangent function has a vertical asymptote. What that means is the graph of the function only exists in between the values, and as you head to the right, it goes to negative infinity, and as you head to the left, it goes to positive infinity. So the graph has to look like this. You can see as we head, it should go through 0. As we head toward the right, so as we approach pi halves from the right, we go to negative infinity, and as we approach pi halves from the left, we go to positive infinity. So it's basically this function. It's periodic because sine and cosine are periodic, and it's got pairs of vertical asymptotes. So you can see here that the lines, odd multiples of pi, are vertical asymptotes for this function. So just remember the limit from the right is positive infinity and the limit from the left is negative infinity. All right, so basically what I want to do now is take a look at another function that's related to the tangent function, and that is the arctangent function. So if I were to look at the limit as x approaches infinity of the arctan function, and then look at the limit as x approaches negative infinity of the arctan function, what would those limits be? Well, consider that if we look at the arctan function, it is essentially this middle strip of the tangent function turned on its side. So the graph of the arctangent would look like this. And the idea is the vertical asymptotes of negative pi halves and pi halves would turn into horizontal asymptotes of pi halves and negative pi halves. So the arctangent function in and of itself will simply look like the tangent function laid on its side, where going to the right, so the limit as x goes to infinity, the limit is pi halves, and the limit as x goes to negative infinity is negative pi halves. And remember, this is the domain of definition for the arctangent. It's only defined, it's defined from minus infinity to infinity, but its range is negative infinity to, is negative pi halves to pi halves. So pi halves and negative pi halves act as horizontal asymptotes for that particular function. So last but not least, I want to take a look at a power function. So we're going to look at the function, it's a reciprocal of a power function. So we're going to look at the limit as x goes to infinity of 1 over x to the n, and the limit as x goes to negative infinity of 1 over x to the n. Now, this particular function looks like the following. So it's a reciprocal. 1 over x to the n would be like this over here, and then like this over here. And so this particular function, you can see that as x goes to infinity, this function goes to infinity. And as x goes to negative infinity, it goes to 0. And as x goes to negative infinity, this function also goes to 0. Coincidentally, the limit as x goes to 0 from the right of this function when you're looking at 1 over x is plus infinity, and the limit as x goes to 0 from the left of 1 over x is negative infinity. But basically the idea here is pretty simple, that 1 over x to the n, as x goes to infinity, the denominator is getting very, very large, which means 1 over a very, very large number is very small in both directions. So both of these values are heading towards 0. This one heads from really big negative values to really small negative values, and this one from really big positive values to really small positive values. But these are the functions that involve limits at infinity that pop up the most often in calculating limits in this course. And so I wanted you to be familiar with each of these functions as well as their limits. Probably best to commit some of these to memory and at least just have a little bit of familiarity with them prior to coming into class. All right, thank you for watching.